Alrighty, so we're going to start our probability unit. And first of all, let's talk about what probability is. We're going to talk about what sample spaces are, what unions and intersections and complements are, and then we're going to take a look at how to calculate and interpret probabilities from some frequency tables as well. Let's first talk about how probability is literally all around us. This is the one thing that you will probably use in everyday life. When we talk about everyday life, we talk about weather. So the percent of chance that it's going to rain or have a tornado or whatever. We could also talk about traffic when we're talking about everyday life. When we're talking about playing some games, you got the lottery that you always hear about. You got some slot machines. And there's lots of other games that you can imply here that involve probability. World events, talk about election polls when we start electing people into office or just voting in general. You have your life expectancy. When you're looking at inherited traits like biology, so like your hair type or eye color, all that stuff we can talk about with probability. It is literally all around us. Biology includes a lot of it. So what is probability? Well, probability is just an outcomes that are governed by chance. When we repeat them over and over and over again, some type of pattern emerges. So eventually we're going to have some type of pattern that's coming out after we repeat something over and over and over again. That is probability. Mathematics help us to understand these regular probabilities and regular patterns that we go through when we're looking at probability. So before we start getting into actually calculating probability, let's go ahead and take a look at some of our vocabulary words that we're going to need to know in order to moving on throughout our probability unit. So looking at a sample space is just all of the possible outcomes that we could have from an event. So we have all possible outcomes here. And when we talk about all the possible outcomes, usually it's going to be some type of list of outcomes that we have when we're going through and calculating or figuring out what the outcomes are. It's just a list. That's what our sample space is. Now, an event is mainly like a subset of the sample space. So it's kind of a specific desired outcome or of a set of outcomes that we want from our sample space. So our event is just a specific or desired outcome, or it's a set of outcomes. Sometimes we want something more than one outcome here. So for our notation, when we start talking about probability, you're going to see something that's kind of similar to function notation when we're looking at the notation of what probability is. So we have a capital P, and then in parentheses A. So what this means is that you have the probability of A or of event A occurring. So we have the probability of event A. This doesn't mean that we're multiplying them at all. It just means a P of A. So we have the probability of event. And usually it's going to be a capital letter A, or sometimes we have some type of capital letter that represents our event, or we just have what is inside there. We want an ace, or we want a heads, or we want tails in our outcome. Once again, it's very similar to f of x, like that function notation, where we have f and then in parentheses x, which is the same thing as y. It just means the probability event. Once again, this isn't multiplying p times a. This isn't multiplying anything. This is just the notation that we're looking at. So the range of probabilities, when we're looking at the range of probabilities in an event, we want to know that the probability of the event is always going to be between 0 and 1. So we can say the probability of an event is between 0 and 1. And this is maybe something that you already knew, but we're going to state it here to make sure that we remember. All right, the sum of the probabilities. So when you're looking at the probability of a whole sample space, your probability should always add to get 1. So the probability of the whole sample space is 1. So all the probabilities should always add to get 1. Think of it's like 100% of the time you're going to have something happen out of that sample space. We're going to have all of our sample space, all those probabilities add to get 1. Now, in our introduction activity, you should have discussed the difference between theoretical and empirical probability. When you're looking at theoretical probability, this is like what should happen. This is the expectation of what we're looking at. So this is like our expectation of what we want when we go to McDonald's. And sometimes reality is, well, we get something that looks like this. So theoretically, or theoretical probability, is what should happen given the sample space. So we want the number of the desired outcomes. So we just take your number of desired outcomes. All divided by your total number of outcomes. So when you're taking a look at the difference between theoretical versus empirical, theoretically, what should happen is your theoretical probability, what should happen. Empirical is kind of when you're performing an experiment, it's something that actually happens. When we have a number of trials that we're doing, this is the reality of it. And it may not be the same, but the more that you do your experiment or your simulation, the closer and closer you're going to get to that true theoretical probability. So looking at your empirical probability, we would take our number of successes divided by the number of trials that you have. And that's how we kind of find our empirical probability versus our theoretical. Theoretically is what should happen. This is what actually does happen in reality when we're given some trials. All right, so let's take a look at kind of like a likelihood number line. That's kind of what we can kind of look at it and see it as. It's like a number line for how likely an event is to occur. So if I have like p equals 0, so the probability is equal to 0, this means my event will not occur. So if I have my probability is equal to 0, well then my event is not going to occur. If my probability equals 1, then my event will occur. And then we have this in between, 0.5. So like we have like a number line here. If we have p equals 0.5, that means the event is equal likely to occur or not occur. So we have the event is equally likely to occur or not occur. Think of it like a 50-50 shot. So if we have like an event going from a probability of 0 to 0.5, we can say that the event is unlikely to happen. Versus if I have something like from 0.5 to 1, then the event is pretty likely to happen. So think of like using this as like a scale reference or a number line to decide how likely it is that the event is going to occur. Now, probability can be written in 3 different ways. It can be written as fractions, decimals, or percents. Either way works. I usually use decimals in this class, and then I just round 3 decimals out just to be safe. Now, if you put 2 decimals, then it's not wrong. It's just 3 decimals. I just like to be safer rather than sorry. And if you put a percentage, not wrong either. It's just a matter of my preference. I like to write decimals and then also round 3 decimal places. So let's take a look at some examples. So in example 1 of probability is that we have a bag of marbles. We have 10 marbles. We have 2 black, 3 blue, 1 red, and 4 white. 10 marbles. All right, and we want the probability that you're going to pull out a white marble. Okay, so we want to make sure that this is a theoretical probability because we're looking at what is theoretically what should happen. So out of the 10 marbles that we have, I want how many are white. Well, that gives me 4 out of the 10 outcomes. There's 10 total outcomes. I could pull out 10 different types of marbles, 4 of which are my event that I want, which is a white marble. So 4 out of 10 would be 0.4. All right, what's the probability that you're going to pull out a blue marble? So pulling out a blue marble, well, still I have 10 outcomes possible, total number of outcomes. Looking at how many blue marbles, though, would be 3 out of the 10. So I have 0.3 when I divide those. Sometimes we look at spinners. So we have in the spinner below, each wedge is equal in the area. So what is the probability the spinner will land on a red wedge? Well, here we have 2 red wedges. Out of the total 1, 2, 3, 4, 5, 6, 7, 8. So out of the 8 total outcomes, I have 2 out of the 8 possible to land on a red wedge or a red little slice. And if I take 2 divided by 8, I get 0.25. What's the probability that the spinner will land on a yellow wedge? So you take a minute. What is the probability that we're going to land on a yellow wedge? Right? I have 3 yellow wedges out of the total of 8. I should get 0.375 when I divide those guys. Now, the probability of a complement is what we're going to be talking about next. So the probability of a complement is the probability that the event does not occur. So it does not occur. Now, to do so, we just take 1 minus the probability of it actually occurring. Or in symbols, what we do, we have probability that it's not, let's say we'll just call it event A, is equal to 1 minus the probability of A occurring. Now, when we're looking at not A, there's a few different ways that people have written this out. But A complement is A and then superscript C. Think of like the C stands for complement. I've also seen like a little apostrophe on the top of the A, but this is kind of standardized, so we'll just stay with the A complement or A or superscript C. So rewriting this in our form in our notation, we have the probability of A complement is equal to 1 minus the probability of A. And we're going to be utilizing the complement a lot of the times when we want something to not occur. Now, sometimes it's easier to compute the complement of an event than the event itself, but that's okay. That's for a different time. Oh, sometimes it's easier to, so there's that little side note for yourself. So looking at your example 3. This is where we're going to start looking at sample spaces, and then we're going to take a look at a probability, and then we're also going to take a look at a complement event. So if I have a sample space, I'm going to flip a coin 3 times, and we're going to have the results of each flip noted. So we'll have flip a coin, is it heads or tails, flip a coin, heads or tails, flip a coin, heads or tails, and that is one event that's occurring. So looking at our sample space, we want to list all of our outcomes. So we can get the first time a heads, we can get a heads the second flip, and we can get heads the third flip. Or we can get heads first, heads second, tails last. We can get heads first, tails second, heads last. We can get tails first, and then 2 heads after that. Or we can get 3 tails, and then we can get 2 tails and a head. We can get a tail, a head, and then then a tail. And then we can also get our heads, tails, tails. So we have 8 different possible outcomes here, and that would be our sample space. That's a list of all our possible outcomes that we have. So now we want to find the probability that a series of 3 flips will produce exactly one head. Okay, so if I take a look at exactly one head, well, this has 3, 2, 2, this has 2, this has 0. This has 1, 1, exactly one head. So out of my 8 total outcomes, I have 1, 2, 3 of which have exactly one head. And when I divide 3 divided by 8, I get 0.375. All right. So when I talk about the probability that a series of 3 flips will produce at least one head, this could be represented by a complement, where the probability of at least one head would be the same as 1 minus, well, what's the opposite of at least 1? It would be no heads. So that would be the probability that no heads occur. Well, if I have 1 minus, the probability no heads, well, no heads at all only happen one time. I just take 1 minus 1/8, and I get 7/8, or divide that out, I get 0.875. Now, yes, you could have counted, so that's why this is a little bit easier to do rather than counting all of these, especially if you have a large sample space. So the complement might be easier to compute than the event itself. So that's what we were talking about up here, is that, well, if I wanted to, I would have to go through and count, okay, at least one head. This has at least one, 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 at least one, at least one, at least one. So it's 1, 2, 3, 4, 5, 6, 7 out of the 8 would have at least one. When I really could just do 1 minus the fact that it never happens, or the opposite of that, which is never having heads at all, which would be 1 minus the 1/8, or the one time that occurs out of the 8 times, and then we have 7 out of 8, and we get the same answer. Regardless, still going to get the same answer. But remember, probability always answers the questions, what would happen if I repeated this many, many times? So what would happen many times? So we're looking for a long-term pattern. Probability always takes a look at our long-term, or in the long run, that is actually predictable in the long run. We're looking for the long-term pattern, but we can use a short-term pattern to maybe help predict the long-term. But it doesn't allow us to make short-term predictions. So remember, we want this to be predictable in the long run, but it does not allow us to make a short-run prediction. Because short runs, it's not really accurate. Remember, it's something called a law of large numbers, where the more I complete the simulation, the more and more times, the closer and closer it gets to the true probability. Now, future outcomes are not affected by the past behavior. So it doesn't tell us what is going to happen in the short run. It always evens out in the long run. So the law of large numbers, the more and more times we do it, and more times that we complete the simulation, the closer it's going to get to that true probability. Probability does not tell us to use it. Does not tell us that it even, or tells it to use it and evens out in the long run as well. So when you've flipped a coin 10 times, right, it doesn't mean, and it was heads every time, it doesn't mean that you're more likely to get tails the next time. This is a false myth of law of averages. So this is not necessarily true, because each flip should be 50-50 every single time. You're just getting lucky here, and it doesn't mean it's more or less likely that you're going to get heads or tails next. So in probability, we also take a look at two-way tables. And we talked about frequency tables back in that should be unit 2. When we discussed two categorical variables. We can use frequency tables and interpret probabilities that way. So we have a group of 50 high school students that were interviewed, and they were asked what their favorite leisurely activity was, and then also whether or not they were male and female were also put into that survey. So it says of all the individuals surveyed, so out of everyone, so there were a total of 50 people surveyed. What's the probability of picking a male whose favorite leisurely activity is dance? So we want male and dancing. So this is a 2. Remember, this is our joint frequency here. So we have 2 out of 50. When I take 2 out of 50, I get 0.04. So our probability of picking a male whose favorite leisure activity is dance is 0.04. So once again, looking at B, we have of all the individuals surveyed, what is the probability of picking a person whose favorite leisurely activity is reading? So we want out of all the individuals, so out of the 50 individuals, how many said that their favorite leisure activity was reading? So reading, 16 out of the 50. Take 16 divided by 50 and use 0.32. So the probability of picking a person whose favorite leisurely activity is reading, it is 0.32. All right, we're looking at part C. This one involves a complement, because of all the individuals surveyed, what is the probability of picking someone who does not consider dance their favorite leisurely activity? Well, we want to make sure that, the probability of not dance is equal to 1 minus, so think of it the opposite way, is the one probability that they dance is their favorite leisurely activity. So I take 1 minus the probability of dancing, which is 18 out of 50. Take 1 minus 18 out of 50 in my calculator and you get 0.64. Now, yes, you could have done this a different way. So if it's not dance, then obviously they like watching or playing sports or reading. So I could have just added the two 16s together and said it was 32 out of 50, and we would get the same answer. But once again, just using the complement and showing that complement exists here when we have not dance, or whenever you see the word not, you should use complement. All right, D is tricky. It says of all the females surveyed, we talked about conditional relative frequencies, which is basically what this is. So of all of the females surveyed, so out of all the females surveyed, looking at just the females, so out of the 30 females, what is the probability you choose a female who likes reading? So out of the females, we want likes reading, so we have the 8 out of the 30. So we take 8 out of the 30, and they have 0.267. So for your practice activity, or practice worksheet, the first question involves a bag of marbles, kind of like what we did earlier. And then the second question involves a deck of cards. You should receive a formula sheet. And some of you know how cards work, some of you don't. On the formula sheet, you'll see all of the deck of cards that you have. So looking at all the deck of cards that we have, you can see that of the 52 cards, because there are 52 cards in a set, each has 4 different suits. So we have clubs, spades, hearts, and diamonds. And each suit contains 13 cards, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 cards, running from ace all the way to king. And you're going to find those probabilities of drawing those cards. And then you also have describing how likely that event is. Remember, using that kind of, so find the missing probability and describe that likelihood of that event. Use that number line that I showed you. And then we also have some dice, and then also a two-way table that you kind of have to fill in for your totals. Alrighty, other than that, if you have questions, let me know.